Yeah, so first I'd like to thank the organizer for inviting me. I don't think I've had a conference that I had so much fun. Today I'd like to talk a bit about some of our work in thermal radiation. And in particular, I'll be talking about two aspects. The first part is about chemical potential for photon, and this part in fact builds upon a very nice tutorial that Professor Zhuoming Zhang gave during the workshop. And then I'm going to briefly talk about some of our work in thinking about thermal radiation related to time-modulated systems. So let me start with the first part. We heard a lot of talk about thermal radiation, and so this is the picture that I like about a thermal radiator. And there are two aspects of it when we typically treat thermal radiation. First of all, we typically assume a Planck distribution with a zero chemical potential for photon. And secondly, in most of the work that you have seen about thermal radiation control, one tends to think more about thermal radiators that are built from metal or from insulators. Semiconductors, in fact, are very interesting thermal radiators. So as a simple example, imagine you have a semiconductor. Ideally, the semiconductor has zero absorption below the band gap, and therefore, if you plot the emission as a function of frequency, theoretically, you are going to see emission immediately above the band gap if the band gap is much larger than KT. So consequently, the width of the thermal emission should also be comparable to the temperature here, and that automatically gives you a narrow band thermal radiation. Moreover, in a semiconductor system, you can apply voltage. For example, you can build a PIN junction, so you have heavily doped P and N regions serving as contact with an intrinsic region in between. When you do that, you can apply a voltage difference between the P and N regions. And in doing so, one separates the quasi-Fermi level of electrons and holes inside the intrinsic region. So in this case, the electron and the hole can radiatively recombine inside the intrinsic region, and with a chemical reaction-like equation as indicated by here, where you have an electron jump from conduction band to valence band to emit a photon. So the point here is that every transition produces one photon. So there is a relation between the number of electron-hole pairs and the number of photons produced. And in doing so, therefore, one can write down the related chemical potential relation, which relate a chemical potential of photon in terms of quasi-Fermi level separation between the conduction band and the valence band quasi-Fermi level. In doing so, therefore, by controlling external voltage, one can impose a chemical potential onto the photon that's being emitted. And so in particular, as was pointed out by Peter Wolfel many years ago, when you look at the emission of a semiconductor under external bias, you need to write a Bose-Einstein distribution with Q times V being the chemical potential for light. So this gives you a number of unusual opportunities. First of all, naturally, at the same temperature, by adjusting the voltage, you can either enhance or reduce thermal emission. If you apply a positive bias, you can enhance emission above thermal equilibrium. And if you apply a negative bias, you can suppress emission below thermal equilibrium. The other interesting aspect, which actually turned out to be quite useful, is to think about this suppression and enhancement process in terms of a equilibrium or a radiant, in terms of what's called a radiant temperature, which is an effective temperature. So the way you think about it is that you write down the emission. Now, you know that the emission is mostly concentrated at a frequency near the band gap. So you can look at the occupation number immediately at the band gap frequency. When you do that, well, this is the standard Bose-Einstein form. But you can say, well, what is an equivalent system of a thermal emitter that would have the same occupation number? When you do that, you get rid of the chemical potential, but you define an effective temperature or a radiant temperature. This radiant temperature is related to the thermodynamic temperature, the band gap of the semiconductor, but most importantly, the voltage that you apply into the semiconductor. So by controlling the voltage here, you have a knob, and a very substantial one, in changing the effective temperature of the semiconductor. And that gives you, for example, very interesting opportunities associated with solid-state cooling. So for example, if you have a hot object and a cold object, in doing cooling, what you would like to do is to pump heat from the colder side to the hotter side. So there are at least two ways of doing so. In the first way of doing it, you can put the cold side as a light-emitting diode or a semiconductor, and then you apply a positive bias so that the radiant temperature is higher than the thermodynamic temperature. And in doing so, you can reverse the heat flow direction and pump heat. Alternatively, you can put a semiconductor on the hot side and then apply a reverse bias to suppress the radiant temperature below this heat sink here. So again, in doing so, you can achieve a heat flow from the cold to the hot. In both of these cases, my former student Kai-Feng Chen has pointed out that you can go to the near field configuration to significantly enhance the power density and also the efficiency of these kind of scheme, even in the presence of substantial non-radiated recombination. I should also point out that the reverse bias case has been demonstrated in the near field by Professor Primo Reddy's group a few years ago. The other interesting opportunity associated with these chemical potential of light is in thinking about non-equilibrium Cashmere forces. So when you think about Cashmere forces, most of the calculation contains the quantum fluctuation. And if you look at a finite temperature, then you have a thermal Cashmere force. Now, if in addition, the temperature of the two bodies are different, then you have a non-equilibrium thermal Cashmere force. And this has been done actually by a number of pioneering works from people in this audience. Our organizer, Professor Anteza, for example, did some of the initial work on non-equilibrium thermal Cashmere force. There have been substantial interest in thinking about these non-equilibrium thermal Cashmere forces. For example, as was also noted, for example, by Professor Manday's work, that if you want to get repulsion in vacuum with regular material and geometry is extremely difficult, but for standard Cashmere force. But if you go to non-equilibrium Cashmere force, it's actually relatively straightforward. And also you can get things like stable equilibrium points that are also very difficult to do with regular Cashmere forces in vacuum. Now, in spite of the interest in thinking about non-equilibrium Cashmere forces, the experimental demonstration has been rather difficult. And at small distances, the quantum or the 0 Kelvin component of the force always dominate. So the thermal part become important only when the separation become comparable to roughly the thermal wavelengths. And if you look at the room temperature, that gives you a length scale of a few microns. But the force itself is already very small at a separation of a few microns to be measured in the first place. And so that's one of the difficulties associated with the thermal Cashmere force. And observing repulsive force in the non-equilibrium side typically also require large temperature gradient maintained at small distances. So the measurement of non-equilibrium Cashmere forces has been actually relatively few. So with this in mind, we can come back to think about this chemical potential for photon argument. And when you look at the radiant temperature description here, what you immediately notice is that with fairly modest voltage on the order of a volt or so, you can get an extremely large radiant temperature of maybe tens of thousands of Kelvin. And therefore, you can actually do a lot of work in non-equilibrium Cashmere forces using semiconductor, but under an experimental condition that perhaps are more readily available. So here was the a theoretical work we did a few years ago with Kaifeng Chen. And so what he imagined is that he had an indium phosphide sphere placed on top of a gallium arsenide plate. And in this case, there are two different configurations. You can apply a voltage either on the plate side or inside the sphere. So when you apply the voltage on the plate, you can actually get a repulsive force at the nanoscale separation of 50 nanometer, which is something that's very difficult to do with conventional non-equilibrium Cashmere forces. If you instead put the voltage on the sphere and you plot the force as a function of separation, you'll see that the force oscillates between positive and negative due to essentially the interference effect as the wave is coming from the light emitting diode hitting the gallium arsenide. And so in this case, there exists multiple stable and unstable equilibrium position as a function of separation. Now, this kind of a multiple stable and unstable equilibrium position is known in the literature for a thermally driven non-equilibrium Cashmere forces. But what we show is that you can see that in a semiconductor situation with very typical parameters that one typically do for semiconductors. So now, let me also comment briefly on some of the prospect of using this idea for chemical potential of photon for energy harvesting. And in particular, I guess Professor Zhuomin Zhang also reviewed this. Instead of doing thermal photovoltaics, where you take a thermal emitter, emit into a photovoltaic cell, Martin Grimm in 2003 has proposed an idea, a very interesting idea, of thermophotonics. In his construction, he replaced the heat source with a light emitting diode under positive bias. As we know, the light emitting diode under positive bias will emit far more compared with a heat source. Now, in this case, however, you would need to drive the heat source to positive bias it, you need to inject electric power into it. So what he did is when he computed the entire energy balance, what he showed is that under the right condition, in fact, you can get far more power this way, even after you subtract the electric power that's injected into the light emitting diode. Now, in his original calculation, what's being imagined is that you would take the power that's generated by the photovoltaic cell and then store those energy into a battery, and then later on you will replace the battery here with the battery that you have originally connected to the photovoltaic cell to basically complete the entire power extraction processes. And so the natural question that will arise is, well, instead of doing so, can you just directly connect the photovoltaic cell to the light emitting diode so that you can directly use the photovoltaic cell to drive the LED in order to achieve a thermophotonic circuit. And we call that a self-sustaining thermophotonic circuit. So in spite of this publication of this paper more than 20 years ago, in fact, in the literature, there wasn't any work that showed you could actually construct a self-sustaining circuit. So my postdoc, Dr. Bo Zhao, who is now the professor at the University of Houston, he was a graduate student from Professor Zhuomin Zhang's group, analyzed this problem. And what he realized was that, in fact, the simplest circuit that you can think of, none of them worked. In other words, you can say, well, let me just directly connect the output of the photovoltaic back to the LED, and you can do that either in series with a resistive load or in parallel with a resistive load. In both cases, in fact, you can show that you would not gain any more power as compared to a standard thermal photovoltaic system. And the simple argument is in fact the following, that, for example, if you look at circuit B, in the ideal scenario, every photon that comes out of the LED is driven by electron-hole pair, and then that photon, when it comes to the photovoltaic, will also produce exactly one electron-hole pair. So as a result, the current between these two are balanced out, and there's no extra current that you can extract from the system to go drive a resistor. And you can give, in fact, a far more general proof about this, even in the presence of non-radiated recombination. So therefore, the key insight that Dr. Zhao had was that one really need to break this balance in terms of photon number between the absorption and the emission process. And the idea that he came up was to design a circuit that looked like this, where the number of LED in series is larger than the number of photovoltaic cell in series. In this case, it turned out that break this balance between the emitted photon on the LED side and the absorbed photon on the photovoltaic cell side, and the extra electron that can be spared to go drive a resistor. And so this gives a self-sustaining thermophotonic circuit. You can just run this by having the LED on the high temperature side, the photovoltaic cell on the low temperature side, and this will connect to drive a load externally. And you can then compute the kind of performance of this system. So here the computation is entirely in the far field with no near field enhancement. What he showed is that if you take 200 PV cells connected in, sorry, not in parallel, but in series, and if the number of LEDs exceed 200 again in series, you will get electric power generation on the order of 15 watt per centimeter square for a hot side only at 600 Kelvin. And this kind of number is represent orders of magnitude enhancement against thermal photovoltaic system. And also it points to the fact that these thermal photonic systems can have performance that are very competitive or even exceeding thermoelectric system in the context of waste heat recovery. So in the last part that I would like to talk about this chemical potential for light, I'd like to give maybe a slightly more experimental, but also a practical example of what we can use this concept for. And this is in maybe a somewhat mundane electrical engineering task of a voltage transformation. So if you go out and look at transmission line, you can still see those on the side of the street. It's very common to see this large magnetic transformer that transforms one voltage to the other. And you do that, this is actually extremely important in both electronic and electrical system because it allows us to basically tailor the voltage to where you would need it. For example, you may want a high voltage for low loss transmission over long distances, but then a low voltage to go drive your electrical circuits and so on. And now, the standard thing that we're used to see is to have a magnetic transformer. So you basically have two coils covered by a basically a ferrite that conduct the magnetic flux and couple these together. Now, in order for this to work, however, this requires you to have a alternate current system or AC system in the sense that the voltage has to vary as a function of time, and this is just a simple consequence of Maxwell's equation. These days, when you look at your own electronic circuits, like the computer that we all have here, the power that's being used to drive it is not AC, but DC. In other words, those are direct current systems where the current doesn't vary as a function of time. In this case, there also is a very substantial need for voltage transformation, but you can no longer use the magnetic core transformer for these purposes. Instead, the standard way of doing so is something called a switch mode converter. And this is basically how the circuit diagram looks like, where you have a switch here, and you basically vary the switch as a function of time so that you periodically charge and discharge the capacitor, and the stored energy there then transform into a voltage boost. So this is a very standard circuit, but it has a number of difficulties. First of all, it uses an inductor, which is actually required for energy storage purposes, because you need an LC resonator for these purposes. And inductors are notoriously difficult for miniaturization integration. Also, the input and output are connected in the same electronic circuit, so there's no input-output isolation. And this is very different from the magnetic core transformer, where electrically the two sides are isolated from one another, and therefore the noise wouldn't go from one side to the other. And finally, the switch here actually induces periodic noises. So to overcome this difficulty, we thought that it would be interesting to do a photonic transformer. So the idea is you take, for example, a light emitting diode, emit light into the photovoltaic cells, and then you connect the photovoltaic cell in series, so that if you put in 1 volt here on the LED, for example, you get a much larger voltage on the photovoltaic cell side. And even though it's a very simple concept, it in fact overcomes almost all the difficulties you can think of about a switch mode converter. There is a natural input-output isolation because the two sides are not connected electrically. From an electronic point of view, there's no switch noise. Nothing here from the electronic point of view is time dependent. Of course, light is time dependent, but that's at a frequency that's very, very high. That's not relevant on the electronic side. And also, most importantly, all these components can be miniaturized and integrated. So we were sufficiently excited about this idea that we decided to try an experiment. So in our experiment, we went and buy 100 LED, gallium arsenide LED, and connected them in parallel. And we also bought 100 silicon photovoltaic cell and connected in series. So here is how the circuit looked like. So here is the gallium arsenide LED and 100 of them. And then this is the silicon photovoltaic cell, again 100 of them. And then we have these two printed circuit board, and then we put one on top of the other. And so this entire configuration looks something like this. And then we measure it. And so for 100 photovoltaic cell LED pair, we get a voltage transformation, enhancement of about 35-fold. This is experiment. So now, it will be interesting then to ask the other thing that that's quite interesting about this device is the noise characteristic. So we also bought a switch mode converter commercially. This is what you can buy. And then what we do is we put a little antenna on top of it so that we can pick up the electromagnetic noise associated with the circuit. Here is one characteristic measurement where we measure the field that pass through this collector. And the blue curve here is when the circuit is not on. And in fact, you just see a blue background, and that's basically the noise of the room. And the red curve here is when the circuit is turned on. In this case, you see this periodic array of spike in the frequency domain, and that basically corresponds to the multiple harmonics of the switching noise. Now, if you do the same experiment with our photonic transformer, so here is the same measurement. And what you can see is that you can turn it on and off. At least the way we measure it, you wouldn't see a difference. So you wouldn't see any of these noises. Now, at this stage, it would be useful to actually comment on existing work on this idea. And people have actually thought about doing the same experiment with laser driving a photovoltaic cell. But fundamentally, on the theoretical side, an LED is actually an engine that can suck heat from the environment, and the laser does the opposite. So thermodynamically, laser is less power efficient than LED. LED has also been thought of, but the difficulty, as it turned out, is that the efficiency for these devices are relatively low. So this we can see in our experiment as well. And even though we get a pretty nice voltage enhancement ratio, the efficiency, which measured as the output power divided by input power, is only on the order of 5%. So now this comes to why I think the fluctuation electrodynamics is interesting. So one of the long-standing difficulty of LED is the extraction efficiency challenge. And roughly speaking, if you're an LED, typically you need to get a photon to go from LED to the air side. And then the interface is between a high index material and the air, and that has total internal reflection. And this has been a long-standing difficulty for LED-like extraction. For our purpose, however, we can do quote-unquote a near-field heat transfer. So what we do is basically we bring the photovoltaic cell and the LED together. But moreover, in this case, unlike almost all your near-field heat transfer experiments, in this case, it doesn't matter that you put a high-index dielectric in between, because you are not doing heat transfer. So as a result, you can look at this probably familiar diagram of the transmission coefficient as a function of frequency and wave vector, and to see that if you put a spacer layer between the LED and PV cell, you significantly broaden the phase space range where you have high transmission coefficient. And this is the kind of configuration that actually can be monolithically integrated. So you could actually imagine constructing, for example, based on gallium nitride platform, of light emitting diode and photovoltaic cell entirely integrated on a single chip to achieve, these are theoretical calculations, of a voltage conversion ratio approaching 100 with about a 90% efficiency, which is a performance that is very competitive against standard switch mode converter, but without all the limitation of those systems. So maybe I will spend the last maybe 5 minutes or so go through the second part of my talk, where I'm going to switch gear and talk about thermal radiation in time-modulated system. You've heard a lot of work on designing photonic structure for emissivity control. These structures are typically static, or even when they're dynamic, you are just modulating it at a time scale that's relatively slow. What I like to show is some of the interesting consequence when you modulate these systems, perhaps on the order of a gigahertz time scale. So in particular, what I'm going to show is that if you take a thermal radiator and you modulate the refractive index of the thermal radiator, maybe on the order of gigahertz or terahertz scale, you can actually operate the structure as a heat engine that operates as a heat pump to send heat from a low to a high temperature reservoir. So as an illustration of the basic idea, imagine that you have just a 2-mode system, a resonator 1 at a frequency omega 1, a resonator 2 at a frequency omega 2, and you modulate the coupling constant between these two resonators. And you choose the modulation frequency to be equal to the frequency differences between these two resonators. Now, this is just a standard, in fact, a Rabi oscillation Hamiltonian, if you're coming from atomic physics background. So let's say at time equal to 0, you have the photon entirely in resonator 1, and as you modulate, you let the time go, then the photon is going to oscillate back and forth between these two resonators. So it goes from 1 to 0, and importantly, the probability of upward and downward transitions are equal. So this curve is entirely symmetric on upward and downward transition. This microscopic symmetry in upward and downward transition is what gives rise to the possibility of building a heat pump. And so in order to see that this alone already is enough to give you a heat pump, what you do is you connect the resonator 1 to a low temperature reservoir at T1, and you connect the resonator 2 to a high temperature reservoir at T2. So in this case, here is the formula of the thermal occupation number. And so if you, for a given temperature difference, if you choose the frequency differences of these resonators to satisfy this condition, and therefore at equilibrium, there are more photons in resonator 1 as compared with the number of photons in resonator 2, for precisely the reason that there's a microscopic symmetry in the upward and downward transition, the net result is that there is a net upward transition because there are just more photons in resonator 1. And so with this, all you need to do is to choose the frequency difference between these two to satisfy this condition. And you can do a more detailed analysis associated with this as a heat engine. So, the amount of heat per transition for a is the basically just taking a photon from here and go up. So this is the amount of heat. And you would need to raise the frequency from omega 1 to omega 2, and the energy that's required, you have to pay, and that's the work that you put in. So therefore, you can compute a coefficient of performance, which is simply the heat that you pump out divided by the work that you pay. And you can then show that given the condition of cooling, this coefficient of performance in fact fall below the Carnot efficiency limit. And you can do a more detailed calculation where you basically plot out the coefficient as a function of frequency difference. And this is where the threshold is, as determined by the temperature difference. At threshold, the coefficient of performance is at a Carnot efficiency limit. And of course, you have zero power, you have zero net cooling. And then as you increase the frequency difference, the power goes up, but the efficiency goes down, as what you typically expect from a heat engine. So this is the ideal case of a 2-level photonic heat pump, but you can actually implement it in a photonic structure. So the way we do it is that we imagine a photonic crystal structure with 2 defects, and these are the 2 resonator modes. One of them consists of lossy material, and the entire structure is also in contact with a heat sink of 290 Kelvin, and therefore this resonator is going to be populated according to this temperature. The other resonator will be lossless. In this case, but it's in radiative exchange with a higher temperature heat source. So in this case, even though it's sitting in a low temperature background, if it's intrinsically lossless, the photon is primarily coming from here. So then we modulate the dielectric function in between these two resonators. And with that, I won't go into the detail of this, but you could indeed, after you compute all the modes and do your typical fluctuation electrodynamic calculation, to convince yourself that this in fact operates as a heat engine that can pump heat out. And moreover, you can go to a near field system. So you can imagine two plasmonic systems putting at different temperature, putting a dielectric region in between, modulate the dielectric region to pump the heat from one side to the other. Now, to summarize this part, it will be useful to compare this idea with other photon-based active cooling schemes. So up to now, there are really two major schemes that people have worked on. One is the electroluminescence scheme, which theoretically has high cooling coefficient of performance, but experimentally, especially in forward bias, is exceedingly difficult due to the need for very high efficiency electroluminescence, external efficiencies. Alternatively, the experiment progress has been largely concentrated in laser cooling. In these systems, the coefficient of performance is in fact relatively low because the anti-Stokes photon and the pump photon frequency difference are relatively small. So this idea of using modulated system to do cooling is interesting because it basically occupies somewhere in between these schemes. It would have a coefficient of performance in principle that can be rather high. On the other hand, this being a modulated system, it does not suffer from the typical difficulty associated with the non-radiated recombination in the electroluminescent cooling. So with that, let me summarize. So I hope to maybe convey that the idea of controlled thermal radiation, which I think is a very powerful idea, can in fact be very fruitfully applied in other areas of research, and in particular, in even thinking about something relevant for electronic circuit, and also going beyond the equilibrium really opens new possibilities. So with that, I'm maybe out of time already, so let me stop, and thank you.
For a couple of questions.
Thank you, very nice talk. I have a quick question. You mentioned you modulated the dielectric function,
yeah.
But you didn't. What's the methodology? What's the mechanism?
So as I mentioned, the modulation frequency is related to the ratio of the temperature. So for this temperature, you would need on the order of a terahertz scale. And in that case, you probably would need to imagine some Chi2 processes, nonlinear optical processes for this purpose.
Yeah, I have a question about the chemical potential of photons.
Yeah.
So in general, when you apply a force to a system, you change the chemical potential.
You change the, sorry?
You change the chemical potential of the system.
Okay.
So the chemical potential is KT, the logarithm of the probability distribution function, plus the free energy related to the force you apply. In the case of particles, F times the displacement.
Right.
So it could happen that the chemical potential is zero, whereas the effect you observe is exclusively related to the force you apply, to the extra term you have.
So
it's perfectly compatible, yeah.
Yeah, I don't disagree. The idea of a chemical potential in this case is really a convenient way to describe the thermodynamics of a non-equilibrium system. You could, as I show here, instead describe them in terms of effective temperature, for example, under certain circumstances, and they're equivalent description, but they're making the same point that if you go beyond equilibrium, there's something interesting to do.
Yeah. And in the effective temperature, you introduce the denominator could be negative, no?
You wouldn't be able to, because the when the voltage is above the band gap, then you get into the lasing regime. That's actually driving a semiconductor laser, in which case the saturation physics actually comes in. Oh. So the V, I should have mentioned this, is this formula. Well, in fact, people do describe an inverted system as a negative temperature. In that spirit, I think it probably is okay, but I'm not 100% sure quantitatively this is okay. So in what I'm treating here, this T star is positive.
Thank you.
Thank you, Shanhui. So what if you change the sign over there? Because Q may be changed, right? Or voltage may be changed. And you get the plus sign. What happens then?
Then it's not too different from a negatively biased system. So you can strongly suppress the emission. So in what we do, in fact, you could either choose the V to be positive or negative already. And if you have a negative Q, then it just flip. So we do both already.
Great, thanks. Interesting, lots of interesting things. I enjoyed it. I was wondering with your photonic, I guess the self-sustained thermophotonic system. I was wondering, is the main complication there also due to the photon extraction from the LED? Or is there anything else that's kind of keeping that from being? Because I noticed with the other system, it had 100 diodes, but you're able to do that. This one, I think it had like 200 or something like that. Yeah. Is there anything that's keeping that from being a reality, or is it?
It's a very good question. Thermophotonic system, if you would like to be able to beat the thermal photovoltaic system, you need to be in a regime where you do electroluminescent cooling. Because you basically say, I pay IV electric power to the LED side. How do I get more than thermal radiation? You get more because you suck heat from the outside. So fundamentally, thermophotonics is a difficult concept because it is the difficulty is directly related to the difficulty of electroluminescent cooling. So yes, so even though we have the circuit, as you can tell, in our lab, we haven't really ventured to do this experiment because we are not sure that you can see the effect that we're seeing here.
Thank you.
I think we have run out of time, right? Because of the shuttle, and they are waiting. So I think we have to close the session. And but you feel free to come here and ask additional questions. So let's thank again our speakers.